So we spent 2 days learning about the graphs of sine and cosine, and I told you in those videos that I really think those are the two most important ones. They're the ones you see most often in our class and in other classes. What I want to do for today for this video is just very quickly go over the key aspects of the other four trig graphs. So let's start with secant and cosecant. And we know those two functions are the reciprocals of sine and cosine. And we're going to use that to do the graphs. So when you're graphing a secant or cosecant function, those graphs come directly from the graphs that we just did, from sine and cosine. So basically, here's the two concepts we're going to focus on. They both have to do with being a reciprocal. Number one, wherever sine or cosine is 0, and that would be an x-intercept on the graph. These graphs oscillate up and down, up and down, up and down. Every time they cross over the x-axis, that's where that function equals 0. Well, where a function is 0, its reciprocal is undefined, and that's going to give you a vertical asymptote there. Now, the second concept is more of a general concept, and it says when you're talking about reciprocals, the bigger a number is, the smaller its reciprocal is, and vice versa backwards. The smaller a number is, the bigger its reciprocal is. And with just those two concepts, you can really quickly and easily turn either a sine graph into a cosecant graph or a cosine into a secant graph. So let me do a quick sketch of each one. Let's say I wanted to do a cosecant graph, and I'm going to start off by drawing a very quick sketch of sine x. So let's say that this one right here is sine x. So the first thing I said is anywhere that graph hits the x-axis or equals 0, our new graph is going to have a horizontal asymptote there. So basically mark each of these intercepts here. Each of these x-intercepts here, there'd be another one about there. Now that's, remember, what I'm saying is the graph that we're looking at is sine x. So what we're seeing is where sine x equals 0. Wherever sine equals 0, cosecant is undefined. You're going to end up with a vertical asymptote there. So you end up with a series of repeating vertical asymptotes. So that's step one. You figure out wherever sine is 0, cosecant is going to have asymptotes there. Now, the second thing I had you focus on, I said, these graphs are reciprocals. So wherever one graph is very small, the other one is very big. So if I imagine this point right here, just to the right, it's on the graph of sine x and just to the right of 0. Your sine graph is very, very small there. It's close to 0. That means your cosecant graph is very, very big. It's way up here, close to infinity. Now, as that on sine, as that point moves to the right, it gets bigger, 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 bigger until it hits 1 right here, and then smaller, 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 smaller. Well, your cosecant graph is going to do the opposite. It's going to start very big, and it's going to go smaller, 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 smaller until it hits 0, and then turn and go bigger, bigger, bigger. So what you get within your set of asymptotes, you end up with these alternating U shapes. Each one, now let me also mention the top and bottom points, the highest and lowest points on sine are where it equals 1 and negative 1. And the reciprocal of those numbers is itself. The reciprocal of 1 is 1, and the reciprocal of negative 1 is negative 1. So each of those points are like the connection. That's where you're on both sine and cosecant. And then you just kind of fill in those U shapes moving away from the graph, because remember, we're talking about a reciprocal here. So wherever sine is small, cosecant is big. And wherever sine is getting close to 0, cosecant is actually approaching infinity, or negative infinity. So basically, the purple graph, the black graph is sine x. That's not part of the graph of cosecant x. I just drew that and used it to draw cosecant x. The true graph of cosecant x is just those alternating purple U shapes that I drew in. The red asymptotes are there to help you see the shape of the U's. The black sine graph is there to see kind of where the u's come from. But the graph itself, like if I just drew cosecant x without using sine to draw it, it would look something like this. It would just have those alternating U shapes like this, and nothing else. So that's really what it looks like. But we use the graph of sine and those vertical asymptotes to help us see the shape. Now, if I want to do secant, I'm going to literally do the exact same thing, but with cosine. So I would draw a graph of cosine x first. Now remember, cosine looks just like sine, but instead of starting at 0, it starts right here at 1. But then it does the same thing. Has that repeating oscillating graph. Sine and cosine look exactly the same. They just start in a different point. Then repeat the same steps you just did. Say each place that cosine equals 0, each x-intercept here, is going to be a vertical asymptote for secant, because 0 and undefined are reciprocals. So let me draw in these vertical asymptotes here. And then for the same reason, you get the alternating U shapes. Basically, the point on the top and bottom of cosine, the points here, 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 for the same reason. Those are where the graph equals 1 or -1, which is its own reciprocal. And then you get those same alternating U shapes for the same reason. Wherever cosine is very small, secant is very big. So as cosine is going towards the x-axis from those points, secant is going away from away from the x-axis from those points. And you get those same alternating U shapes like this. So again, the graph I drew you looks kind of messy because you see everything. You see the graph of cosine, you see those vertical asymptotes. If you were to like type into Desmos just y equals sine x, the only thing you would see is those U shapes. So you'd have one right here and one right here, and they just alternate, one on the top, one on the bottom, like this. So that's what secant and cosecant look like. They are alternating U shapes, one up, one down, one up, one down, and they have those skinny U's that are kind of squeezed between vertical asymptotes, and each one starts from the very top or the very bottom of the reciprocal graph. Okay, now I'm not going to spend a ton of time on this, but just think about what we did with sine and cosine when we did period and amplitude and phase shift and all that stuff. If you ever have those types of transformations to a secant or cosecant graph, just do the transformations to the reciprocal graph, and then after all the transformations are done, that's when you draw in those U shapes. That's when you do the asymptotes and the U shapes. So don't ever try to do like period or amplitude for a cosecant graph. Say, I'm just going to do all that work for the sine graph. And then after I've done the work for period, amplitude, phase shift, then I'm going to convert that sine graph into a cosecant graph. All right, so let's switch gears and talk about tangent and cotangent graphs. These are very different. So we did our sine and cosine graph. We did secant and cosecant and said those come directly from sine and cosine. Tangent and cotangent are very different. So number one, like secant and cosecant, they also have asymptotes. Like for example, tangent is sine over cosine. So anywhere cosine is 0, tangent is undefined. And cotangent would be the opposite. It's the reciprocal, so it's actually cosine over sine. So anywhere where sine is undefined or is 0, cotangent would be undefined. So yeah, what I just said for a second ago for tangent, wherever cosine is 0, tangent is undefined. And for cotangent, where sine is 0. Now, for tangent, you get these funny shaped graphs between the asymptotes. It looks a lot like x cubed. I said x squared. Let's fix that. Not x squared. They're not parabolas. It looks like x cubed. It has this graph that twists and kind of goes up in one direction and down in the other. And cotangent is the exact same, but it's been reflected. So it goes up in the opposite direction and down in the opposite direction. And I'll give you a quick sketch of these two, just like I just did for secant and cosecant. So let's start with our tangent graph. If I wanted to graph tangent, remember the key here is that for any variable, we'll call it x, tangent is sine over cosine. So wherever cosine is 0, tangent is undefined. Now from the unit circle, cosine is 0 at pi over 2 and 3 pi over 2. But then remember that repeats, so it's also negative pi over 2, negative 3 pi over 2, 5 pi over 2, dot, dot, dot. So just from the unit circle, you get these two values here, which if I mark them, let's say this is 1 pi right here and this is 2 pi right here, you're basically putting an asymptote halfway between each pi. And then you could do the same thing on the negative side. So at every half pi, 1.5, 2.5, 3.5, if you think of it that way instead of like 3 over 2, that's where your asymptotes are. Now between every set of asymptotes it looks the same, and this is what tangent looks like. This is what I was saying. You have this point right smack in the middle, and then you have this twisting graph that actually looks a lot like x cubed. It twists up towards this asymptote and down towards this one. And then what you have is that repeating shape in every little section. Every section of asymptotes looks exactly the same, or between each two consecutive asymptotes. It looks exactly the same. So for tangent, you get this repeating sort of x cubed looking graph over and over and over and over between each two asymptotes. Now let me do cotangent real quick. All right. So for cotangent, now remember, tangent and cotangent are reciprocals. We know that tangent is sine over cosine. That makes cotangent cosine over sine. Which means for our asymptotes, this is why I said on that 2 slides ago, I said cotangent has asymptotes where sine is 0. Now from the unit circle, that happens at 0 and pi. But basically it repeats. So it's actually a little easier even than tangent. It's every whole numbered pi. It's 2 pi, 3 pi, dot, dot, dot. It's negative pi, negative 2 pi. So for cotangent, you get an asymptote right down the middle. And if I count by pi again on my x-axis, it's basically you get an asymptote right on the whole number pi. 1 pi, 2 pi, negative 2 pi. Now, just like cotangent, if you focus on any two asymptotes, pick any two. Right in between the two, you get a point right here. Now for cotangent, you get the exact same shape as tangent, but in the opposite direction. It's up to the left and down to the right. It's a reflection, basically. And then you just recopy it in each interval. Now, for cotangent and tangent, I'm not going to spend a lot of time about transformations. Basically the same transformations we learned for our other 4 graphs work. Like if you take the x and multiply it, it might change the width of the asymptotes. Or if you take the function itself and multiply it, it might stretch it taller. I'm not going to spend a ton of time on that because, like I said, I would rather that with the limited time we have, you guys really focus on the sine and cosine graphs and really become an expert on those. But I wanted to at least introduce these 4 graphs to you so you can see what they are, kind of where they come from, and so you'd recognize them. Like if you're seeing a question and you see this graph right here, at least it'll kind of be there in your head, be like, I remember that one. That's some sort of cotangent graph. Or if you see it with the ones going in the opposite direction, up to the right and down to the left. Again, you'll look at it and be like, yeah, I kind of remember that one. That's a tangent graph. Or those alternating U-shapes, it's one of the reciprocal graphs. I want you to recognize them, but I'm not going to spend as much time as it. I really want to focus on the sine and cosine graphs and have you guys master those.